when we talk about an indexed collection of sets, what we're trying to do is we're trying to come up with a way of discussing not just one set at a time or two sets at a time, but we want to be able to put an entire infinitude of sets down on our table, our laboratory bench in front of us, and to be able to talk about a whole infinite collection of sets and the properties that they might have in common, what we can do with them, and so forth. This is useful for a wide variety of different reasons. Looking ahead at your course in real analysis, for example, in the Math 401, one of the ways that we can define what real numbers are is we can define them by analogy to sets. And so, in a way, every real number is a set called a Dedekind cut. And so there are infinitely many different sets that index the different real numbers, right? So that's just kind of one example of why we might talk about an indexed collection of sets. But the hardest thing, of course, about infinity is that we can never see it all. We can never write it all. We can never understand it all. And so we have to use notations. We have to use ways of expressing an infinite collection of sets in as compact of a way as possible. So what we often do is we index an infinite collection of sets using an indexing set. So what I want to do is work through an initial example together. And then we'll give you the opportunity to work on a couple of examples in breakout rooms that I'll float back and forth between today. And this is really my only agenda for today. It's like one problem together and then one problem in our breakout rooms. And that's going to take us the full class period today. Just because, as usual, wading through the notation, I think, is the hardest part about working with sets in general, but in particular index collection of sets. So let's take a look at what it looks like. We'll do that with reference to this first example here. What we're doing in this example is saying for every integer, so you give me an integer, we call it n. Every integer is going to correspond to a set, and the set that it corresponds to is going to be the set with 4 elements in it, and those 4 elements are n itself, and then 1 more than n, 2 more than n, and 3 more than n. Right? So any integer you give me, I'm going to give you back a set that has 4 elements in it, and those are the 4 elements that it's going to have. And so what we're going to want to do with this collection of sets, we've defined now infinitely many sets, one for every integer in the set of integers. So that's a lot of sets that we just defined. And we want to be able to do operations with that collection of sets. And the advice that I'm going to give, and these problems are very well scaffolded out for us to kind of think through this in this way. The advice I'm going to give is to try and first be concrete. Get your hands on what a few of these sets, sort of representative sets, look like. Try and get that in your head numerically. Try and get a picture on the page that helps you to understand what these sets are and how they relate to one another. Because the better the quality of that picture, that understanding, then the much less work that we're going to have to do to understand how to do operations with those sets. So the first thing that I'm going to want to do here is just write down a few examples of what are these sets that are being discussed. And then once we've gotten that understanding, we can go forward and actually do some operations with it. So for starters, let's just take this pattern that's being described by this indexed collection of sets. And then let's just write down a handful of different examples, which is what we're kind of being asked to do in part A here. So if you give me a different integer, I should be able to give you a different set. So let's say you give me the integer n equals 1, or you give me the integer n equals 3. Or, because the integers include negatives as well, you give me the integer negative 2. Maybe I'll also put positive 2 in here. Let's put as many examples as we can kind of stomach so that we can understand the basic pattern of what's going on. So for each of these integers, n, what we're being asked to do is to build a set that has 4 elements in it that consist of n itself, but also 1 more than n, 2 more than n, and 3 more than n. So corresponding to the integer n equals 1, we're going to have a set with the following 4 elements. N itself, first of all, so S sub 1 is going to consist of n itself, which in this example is 1, but also 1 more than n, 2 more than n, and 3 more than n. Right? So if you give me the integer 1, I'm going to be giving you back the set whose elements are 1, 2, 3, and 4. Similarly for n equals 2. I'm going to go through these a little bit quicker now. For n equals 2, the set S subscript 2 is going to have 2 as one of its elements, but then also 1 more than 2, 2 more than 2, and 3 more than 2. So the elements in S2 are 2, 3, 4, and 5. What makes the notation, I think, so challenging about working with indexed collection of sets is just the fact that we're always going to be carrying these subscripts around, right? The set S subscript 1, S subscript 2. So just remember, just refer back to how these collections were defined to remind yourself what that subscript actually means, right? What we might say is that that subscript in this example is telling me what is the smallest, what is the least element in this collection of 4 integers, n plus 1, n plus 2, n plus 3. So S sub 3 is going to be 3, but also 4, 5, and 6. N equals 5. S sub 5 is going to have 5, 6, 7, and 8. And because integers include negatives as well, we also have sets like S subscript negative 2, which looks kind of funny, but it's totally in play here, right? Because we have indexed our collection of sets using the integers as our index set. So we will have an S sub negative 2. We will have an S sub 0. We will have an S sub negative 155, right? All of those different integers, each one of them has its own set. And so we'll have negative 2, but we'll also have 1 more than negative 2, 2 more than negative 2, and 3 more than negative 2. So anytime, and I still do this as a professional mathematician, anytime I'm working with an indexed collection of infinitely many sets, I don't try to do anything with it until I first understand for myself, what do these sets actually look like? What relationship do they have to one another? So I'll write down a few examples like I've done up here. But then very often I'll also, because I tend to prefer visual modes of communication and understanding whenever possible, I also like to come up with a sketch of what these sets might look like. And so since all of these sets are subsets of the integers, and in particular subsets of the real numbers, let me just put a real line in here for the moment and try and sketch out what these sets look like with relation to this same real line. So on my real line, I'll mark a 0 somewhere. It's over here. 1, 2, 3, 4, 5, 6, 7, 8. I'll go backwards. All right, so here's a real line. And then the first thing I'll do is just say, well, where are my elements from S1, let's say? How could I sketch the set S1? Well, it consists of the integers 1, 2, 3, and 4. So these 4 elements, that's my set, which I'm going to call S1. So that's what S1 looks like. It's these 4 disconnected points on the real number line. And I'll keep going. So S2 is 2, 3, 4, and 5. So 2, 3, 4, 5. There's my S2. S3 is 3, 4, 5, and 6. And so we're beginning to see this picture emerge that each one of my sets, S sub n, is sort of just a copy of the previous set, S sub n minus 1, just sort of nudged over on the real line by 1. Let me add in some tick marks here just to make it a little bit easier to read. 5, 6, 7, 8, negative 1, negative 2, negative 3. And so this green collection of 4 dots here is the set S3. S5, so I was just picking some random examples here. S5 is 5, 6, 7, and 8. And so S5 is over here somewhere, 5, 6, 7, 8. There's my S5. S negative 2 is negative 2, negative 1, 0, and 1. And I'm kind of, in my diagram, I'm putting each of these at a different height just so that I can more easily tell them apart from one another. If we tried to draw them all on top of the real line, it would just get really cluttered really fast, I think, and it would get hard to understand what the relationships are. So anytime I'm doing a diagram like this, I try and separate all of my different sets just by giving them some vertical height so we don't have to draw them on top of one another, because then we get super confused. So there's this picture for these sets that each of the sets is just 4 consecutive integers. And as the index, as n gets bigger, those integers are just sort of further up the number line. If n gets smaller, lesser, then it's further down the number line toward the left. And so this is kind of a picture of what this infinite collection of sets looks like as far as some of its individual elements. Sorry, individual sets in that collection. So now that we have our hands on what this collection of sets looks like, we can do set arithmetic with these sets. We can do unions. We can do intersections. We can do also, what we would hope to be able to do, is we hope that we can also do unions and intersections of the entire infinite collection of sets. So that's really the one thing today that's a little bit new compared to what we were talking about a week ago. A week ago, we talked about the concept of union and intersection for just finite collections of sets. If I union 2 sets together, what do I get? If I intersect 3 sets together, what do I get? Today, when we have an infinite collection, we want to be able to say, what do I get if I union all infinitely many of these sets together? Or what is going to belong to the entire infinite intersection of this entire collection of infinitely many sets? That's today's degree of difficulty, and that's where we're getting to in part D and E of this exercise. But as with anything infinite, in order to get there, we want to first do a couple of small finite examples to understand what's going on. So that's what parts B and C are going to help us to do. Describe the union of S1 with S3. The first set in the collection, quote unquote, and the third set in the collection, quote unquote. So if I took the union of S1 with S3, record that off to the side underneath me here, S1 union S3, well, if I didn't have my picture, I would just do this by writing out the rosters for these 2 sets. S1 had a roster of elements 1, 2, 3, and 4. S3 had a roster of elements 3, 4, 5, 6. And so even if I didn't have my nice picture, I could just do this using the rosters and say, well, S1 union S3 is going to have the elements in a union consist of all of the elements of the original, all thrown together into one bucket. And so S1 union with S3 is going to contain 1, 2, 3, 4, 5, and 6. And another way for us to see that would be to just imagine that we took these elements from S1 and these elements from S3, and we just piled them all in together. And sometimes I will draw that right down on the number line. So I'm going to have 1, I'm going to have 2, I'm going to have 3, I'm going to have 4, I'm going to have 5, and I'm going to have 6. It's a bit like saying I'm going to get an element in my union as long as that element exists in even one of the sets that lie above me, right? So all 4 of these, we push them down to the number line, and then all 4 of those, we push them down to the number line as well, and then we take everything that we got and pile it all together into the union. That's visually how I usually think about taking the union of subsets of the real number line, is sort of stack them together on top of one another and then sort of push everything down onto the real line and see what we have. We can do a similar kind of thing for intersection. We just have to use intersection logic, intersection thinking, instead of union thinking, right? Instead of thinking about piling all the elements together, for an intersection, we ask that critical question, what do these sets have in common with one another? Sorry, let me... So let's tackle that second part of this problem, which asks us to find, and this notation is a little bit weird, so this notation is also perhaps a little bit new for us today, so we'll unpack the notation. But the way that I would read this, again, how you read it in your own head very often is the first step to understanding it correctly, what's being conveyed here. How I read this is that we're talking about the intersection. So that's this big upside down cap sign, right? The intersection of the sets S sub I for all of the i's beginning from I equals 1 and ending at I equals 3. Right? So this is very much like the sigma summation notation that you get when you're adding together a bunch of numbers, right? The lower limit here, the lower subscript tells me which version of I I'm going to start with. So I is going to go as low as 1. And the one on the top tells me how far up the i's are going to go. So I from 1 up to 3, we want to take the sets S sub I and intersect them all together. So just to unpack that again in notation, this will be a big intersection sign with an I equals 1 underneath it and a 3 on the top. And then we have S sub I. So I'm going to expand this out. So what is meant by this? What's meant by it is I'm going to take the sets indexed by the values of I from 1 to 3. So that includes 1, it includes 2, and it includes 3. I'm going to take the sets whose name is S sub I, so that means we'll have S sub 1, S sub 2, and S sub 3. And what am I doing with them? I'm intersecting them all with one another. So that's all that this notation meant, right? The intersection from 1 to 3, from I equals 1 to 3 of the SI's just means S1 intersected with S2 intersected with S3. So anytime you have that weird looking big union or big intersection style of notation, often just writing it out, getting rid of that weird subscript I and just writing it out explicitly is a good way to make sure that you're doing the right thing. So now we understand what three sets that we're working with. I've got this set right here, S1. I've got this set, S2, and I have this set, S3. Those are the three sets that I'm supposed to now be intersecting with one another. So if I want to intersect all three of these sets together, I need to apply the AND logic instead of the OR logic, right? The OR logic was for unions, AND logic is for intersection. The elements of the intersection are those elements which belong to S1 as well as to S2 as well as to S3. Only those elements which belong to all three of those sets will belong in the intersection. So for an intersection, I'm going to go down to my real number line and look up and say, are there any elements which belong to all three of the sets that I'm intersecting together? If I ask that question about 1, the answer is no. It belongs to S1, but not S2, not S3, so it doesn't belong in the intersection. Same thing with 2. It belongs to 2 of those sets, but not the third, so 2 doesn't belong to the intersection. It's not till I get to 3 that I look up and I say, oh, look, 3 actually belongs to all 3 of the sets that I'm intersecting together. And therefore, 3 is going to be one of the elements in my intersection of these 3 sets. And then we end up saying the same thing about 4 as well. But that's all, right? 3 and 4 are the only elements for which we can look above us from the number line and say, yes, this thing actually belongs to all of the members of the collection that I'm intersecting together, and therefore it belongs in the intersection of all 3. 5 doesn't belong because it's missing from S1. 6 doesn't belong because it's missing from S1 and also from S2. So the intersection of those 3 sets consists of just the numbers 3 and 4. Let's tackle the infinite question. And we'll start with the infinite union. So that's the notation that's being used here in part D, right? Here this says, find the union of the sets of the form S sub n, so the members of my collection, where n ranges over all integers, right? So one of the ways that we could expand on this, n belongs to the integers of S sub n, we could see this as saying we're going to take the union of S sub n for all integers n. So we're going to take the unions of all of the integers S sub n up to S sub minus 5, S sub minus 4, S sub minus 3, S sub minus 2, union S sub minus 1, union S sub 0, union S sub 1, union S sub 2, union ... Right, so it's this huge, gigantic, massive expression. If we were to try to write it all out, it would be by infinite, right? Because there are infinitely many integers kind of going in both directions on my number line. But what we're really asking, when we're asking for the infinite union of this collection, I like to think of it as the following question. I'm going to ask myself, what are the elements? How would we describe the set of all elements that belong to at least one of my sets? After all, that is what it means to belong to a union, right? If I belong to a union, all I have to do is belong to one of the sets which is participating in that union. As soon as I belong to a single set in this collection, then I belong to the infinite union of the entire collection, right? It's just an everybody in the pool kind of thing. So remember when we were looking at the number line before and doing a union, so let me go back to the union version of this number line diagram here, if I can. Kind of put this back the way that it was. When I was finding the union, I was saying, well, as soon as even one of the sets in my collection has a dot where I am, then I'm going to belong to the union. So 1 is going to belong to the infinite union because it belongs to the set S1. 2 is going to belong to the infinite union because it belongs to the set S1. -1 is going to belong to the infinite union because it belongs to the set S -2, right? And so on and so on and so on. And so what I would ask myself if I'm figuring out this infinite union is sometimes I ask, well, is there anything that doesn't belong? Is anything not going to belong to the union of infinitely many of these sets? Are there any places on the real number line that are not going to have any dots from my sets sitting above me? And there's definitely some spots on the real number line that don't, like 1/2, for example, doesn't belong to any one of these sets in my infinite collection. So 1/2 is not going to belong to the infinite union. But in fact, any integer at all, I'm going to be able to find that integer within at least one of the sets in my collection. Like if you ask me whether or not 174, the integer 174, belongs to this infinite union, I can answer that question. Does 174 belong? In order to belong to the infinite union, I just have to find even a single set in my collection to which it belongs. And there could be more than one answer. In fact, in this example, there is more than one answer. But what is just one example of a set in my collection of which 174 is going to be an element? The number 174 we know for sure is going to belong to the 174th set in my collection. Why? Because what is my 174th set in my collection? It's 174. Its elements are 174, 175, 176, 177. Right? So 174 definitely belongs because it's going to belong to S sub 174. And so we can kind of make the argument here that any integer that you give me, for any, let's call it k in the integers, does k belong to my infinite union? Yes, it does. Because, in particular, we know that k is going to belong to the set S sub k. So what this argument tells me is that every integer can be found in this infinite union. So how could I express that using what we know about sets and notation? If I know that every integer is going to be an element of this infinite union, what am I really saying using the vocabulary that we've developed so far about sets? If I say that every integer, every element of the set Z, is an element of this infinite union, then what I'm really saying, using the vocabulary of our course, is that the integers are a subset of this infinite union. So we have gotten at least part of the way to describing what's in this infinite union. We know every integer is going to belong. What about everything that's not an integer? Is there anything we can say about the non-integers? Is there going to be any non-integer that belongs to this infinite union? Great. Definitely we are not going to have any non-integers in this infinite collection. Why not? Because each of the individual sets in my collection consists only of integers, right? And so if I take the union of a bunch of elements which are subsets of if I take a union of a bunch of sets which are subsets of the integers, I know for sure that my infinite union cannot be any bigger than the integers itself. We're never going to find a non-integer inside of this infinite union because we're not going to find a non-integer in any one of the sets which comprise this infinite collection. And that is an argument not that the integers are a subset of this infinite collection, but actually that the reverse is true also, that this infinite collection is going to itself be a subset of the integers as well, because it consists of only subsets of the integers being unioned together. And so since we can argue that each one of these is a subset of the other, we've therefore proven that these sets are equal. And so the question, what is the infinite union of this collection of sets? The union of this infinite collection of sets is the set of all integers. To determine the intersection of an infinite collection of sets, we have to ask ourselves the other question, not what elements belong to at least one of the sets in the collection, but in order to belong to the intersection of infinitely many sets, I have to be an element that belongs to every single one of the sets in my collection. Are there any elements that belong to every one of my sets? Is there anything that all of my sets in my collection can agree upon? And so in our example, let me take away this piece that's underneath here. Let's pick on a real number. Let's say we pick on 0 for a moment. I want to ask the question, does 0 belong to this infinite intersection? Does 0 belong to every one of the sets in my collection? Can I find even one example of a set to which it doesn't belong in my collection? So 0 does not belong to the infinite intersection because we can find an example of one of the sets in my collection, namely S1, of which 0 is not an element. Right? And as soon as 0 doesn't belong to even a single one of the sets in my collection, that means it doesn't belong to the infinite intersection. Because to belong to the intersection, it has to belong to every one of the sets. So 0 doesn't belong. Whatever this infinite intersection is, it doesn't contain 0 as an element. What do we think it does contain as an element? So if you give me any integer k, I'm going to tell you k cannot belong to this infinite intersection because, in particular, it's not going to belong to the k plus first member of this collection. Because the k plus first member of this collection is going to consist of k plus 1, k plus 2, k plus 3, and k plus 4. It's not going to contain k. Right? So no integer that you could give me could belong. Right? What about any non-integers? Can I get a non-integer here? Does any non-integer belong to every single one of these sets?
No.
No, because no non-integer even belongs to a single one of these sets, right? As we were arguing before when we were working on the infinite union. So what elements do belong? Or maybe I'll say it this way. What is this set?
Yep.
Yeah. There's nothing. There are no elements that belong to this infinite intersection. Because if I'm an integer, I belong to exactly 4 of the members of this collection, but infinity minus 4 of them do I not belong to, right? Which is more than enough to show that no integer belongs, because even a single set to which it doesn't belong means that it doesn't belong in the infinite intersection. And then no non-integer is going to belong, because no non-integer belongs to even one of the original sets in my collection. So the infinite intersection of this collection of sets is an empty set.